Howdy. Howdy. Always works. Thank you so much. We're so happy to have the first laser talk in this new season. I'm the director of the Institute for Applied Creativity, Hwa-young Seo. We host the laser series. This event has been supported by the university galleries, as well as College of Performance, Visualization, and Fine Arts. I'd like to introduce an incredible team of us. Dr. Lynn Vatan, also Shipra, Sinha over there. Without them, we couldn't do any of this work. I really appreciate your support. We also have supports from the college, John, and also Hunter's group and Justin's group. I really appreciate that. With that, I'd like to invite Dr. Vatan to introduce more about the laser program, as well as introduce today's speaker. Thank you.
Thank you, Hwa-young. Welcome, everyone. We are so happy you're here. We know how valuable your time is and how there are a million things going on at all times. So students, faculty, friends, community members, thank you so much for taking the time to learn and share and explore some amazing work. So my name is Lynn Vartan, and Hwa-young and I have been running this series now. This is our second semester. We started in January of this year and ran for a semester, and now we have an entire year of events for the academic year, and this is our kickoff. The laser series is really in the spirit of Leonardo, and it goes with the Leonardo Publishing Group, and it's meant to be a focus on interdisciplinary activities and how that might translate into our work. So we're particularly looking at intersections between science, technology, arts, everything that we can think of, and that's such a great fit for our college and such a great message. This is what we live and breathe, so this is what we want our speaker series to really embody. So that's a little bit about the speaker series. We happen just basically once a month here in the Start Gallery in this beautiful environment surrounded by art and sharing. So the format is about a 30-minute talk followed by a little bit of a talk and Q&A where we can get into a little more personal conversation. If you have questions, we can kind of stretch out a little bit. So it's a little different in that structure. So with that, I would like to invite Texas's very own faculty member from engineering, and she's going to tell you all about all the amazing things that she does. Kiju Lee, welcome.
Thank you so much for the invitation and the introduction, and I'm really happy to be here. This is my first time at this gallery, and I walked by, but I never actually had a chance to actually come in, and this is beautiful environment, and I am glad to have this opportunity to share my research as well as some of my kind of side part of research that is connecting robotics with art. So today, my title is From Soft Robotics to Robotic Art, in particular applications of origami. But I'm going to start by introducing what I do in my research lab. So my lab is called the Art Lab, so that makes a good name. So this, I know many of you are interested in interactive art, media art, and those kind of the real art, but this actually, art doesn't stand for that art. It's actually an acronym of Adaptive Robotics and Technology Labs. So when I moved to Texas A&M, so I had a chance to actually establish a new research lab, and before I had my research lab called the Distributed Intelligence something blah blah, and it never made actually good name, good acronym. So I wanted to actually come up with something really kind of simple, short, but easy to remember, so that it actually made art, and that reflects many of those aspects that we do in our lab. While it's not only just about aesthetic art, but art is applied to kind of engineering. So whenever you make it, I tell my students saying whenever you make a robot looking good, actually it works better too. So I'm gonna share some of my research first, and then I'm gonna actually introduce how we basically have some of those robotics design that is inspired by origami that translated into a research problem. So in my lab, we work on a diverse range of robotics research. So we do we build mobile robots with reconfigurable wheels. We build a kind of low-cost humanoid torso type of robots that can be a do-it-yourself type of project. So you can build a robot with a few $100s, and then you can actually implement different codes and AI algorithms to test it out. We build tangible games that is designed for the cognitive assessment, initially designed for young children where the language development is delayed. Then you cannot actually implement cognitive assessment tools. So you can actually use the tangible tools and block games to use it for assessing their cognitive developmental stage. We later developed into the games that can be used by traumatic brain injury patients as well as older adults. But also we have been applying design principles or different design inspirations into robotic mechanisms that is different from traditional like a rigid body or a very link-based kind of robotic structures. So one of the inspirational overarching theme of my research lab is design-driven innovation. And I'm going to first share some of our recent work that has been done over the past few years. We applied the design-driven innovation to advanced ground mobility. So one of the examples is this mechanism. It's a wheel that has a few gears. So it consists of a central gear that connects to the motor that will make the wheel roll. And it has leg segments with the partial gears. So whenever the driving gear rotates, the leg segments opens up. And then it can close as well. Depending on which direction this wheel is rolling, it may remain seamless circular wheel or it could open up. So this idea is basically having reconfigurable or transformable wheel mechanism, purely mechanical design that can be applied to a robot or any other kind of rolling mechanisms that could be potentially used for diverse applications. Based on our knowledge, this is one of the simplest transformable mechanisms out there, and then that can achieve the actual transformable behavior and multi-terrain mobility on diverse surfaces. So we actually proposed this concept to DARPA so that there were basically a few years ago, DARPA was seeking for a solution to advanced ground mobility that can be used for wheeled robots. There was a specific program called OFFSET, Offensive Swarm-Enabled Tactics Program within DARPA, and they were using hundreds of wheeled robots for basically covering large area for various urban military missions. And those wheeled robots, especially when they are in a smaller form, they cannot go over any small kind of obstacles. And when you think about everywhere, the staircases, whenever you think about urban environment, staircases are ubiquitous in both outdoor and indoor. And also there are small, any rough environment, small wheels cannot overcome. So we basically proposed this idea to DARPA. So we're gonna build this kind of robot with those new type of wheels. It's gonna go over different types of terrains, go over obstacles, and then staircases. And it's not gonna add any additional motors, actuators, sensors, or control needs. It's gonna operate exactly the same way as wheeled robot. So that leads to our new robot that is called Alpha Walter. It's adaptive wheel and leg transformable robot that is the outcome of our DARPA project. So this robot, equipped with various sensors, it has the capability to autonomously perceive the environment and actually determine which direction to go. So autonomous navigation, perception, and also stair climbing, as you can see. This one was the first time this robot was actually introduced to public at the conference that was invited by Jeff Bezos, if you may know, from Amazon founder. So it was a little bit risky because when we got the invitation to present this robot at this conference in front of Jeff Bezos as well as many other people who were attending the conference, it was just at the beginning of the project. So we didn't have the working robot, and they invited us because they read a news article about this project launching. So I said, so when is it? So it's about 6 months from now. And either way, because DARPA wanted us to build a robot within 6 to 9 months. So that is incredibly short time period if you think about research lab, a single PI-led academic-based research lab. But we already promised to DARPA, so if we are gonna deliver this robot to DARPA, we should have it ready, so by that conference date. So we said yes, but it actually worked out. So we made it everything and tested on campus and diverse like staircases. So we brought it to the conference, and the robot actually made it to the stage. So that was kind of really interesting exposure and first debut of the robot. Now we also have additional newer robot that is called Claw. Another design-driven innovation applied to the mechanical kind of, reinventing the wheels. This is actually a combination of a regular wheel together with a bar mechanism that allows the claws to come out and retract back. Whenever you see those kind of mechanisms rolling around, it actually, whenever it goes and then approach near the ground, it tracks back. So it never touches it, but whenever it is encountered by an obstacle, it's going to actually engage and scale over the obstacles. So this is another kind of robot embodiment we did for this claw mechanism. You can see it smoothly rolling over. We just operated in a slow speed, so you can see that the actual climbing motion is relatively smooth, and also it achieves a diverse kind of locomotion capabilities that we are expecting. And this is much higher kind of it can cover very diverse terrains. If a small wheeled robot can go over staircases, they are likely to kind of traverse many different and challenging terrains. So we are building an individual robots with different kind of mobility, and these are two of the examples that we built in our lab. But again, we're building many different types of robots, and each of them carries their own capabilities and different limitations and different kind of specialized functionalities. One of the kind of biggest challenges that we are interested in tackling in our research program is that many real-world problems are often too complex for a single or a few robots to handle. Some of those examples, you may need to actually cover a really expensive, large area within a short amount of time. So if you have to dispatch a kind of, a troop of like soldiers to an unknown environment, or if you have a large kind of, the power plants that needs to be covered or inspected for certain types of risk, you may not be able to send humans immediately. You want to send robots to cover and actually report back the information about those sites. Many of those tasks involve complex environment involving dynamic situations and uncertainties. So sometimes you may need to actually scale up or down depending on the complexities and also the size of the actual task as it goes. So sometimes you need to have more robots to do it. And then if you dispatch 20 robots and then you find out something going on and you need to actually call for some others to help with the actual task or mission to be completed. And also some of the situations you need redundancy in the information. So not only a single robot inspecting and making the decision, but you may need multiple robots coming together and do it. Because whenever you see something unusual, usually what you do is you call people around, look at this, look at what's happening. So you want to basically confirm and reassure what's going on. So that's basically what the robots can do in case of any kind of emergency or certain situations that requires redundancy in the information. So the actual bigger research topic we work on is swarm robotics. So robotic swarm is an ultimate integration of swarm and intelligence and engineering. So intelligence side, you may consider many different problems starting from a decision making. If you have many simple robots, how do they make decision? If you have multiple options to choose from, how do they make the best decision out of those choices available? How individual robots, they basically communicate with each other, and what kind of individual capabilities, and how do they basically share this information must be tackled within the engineering domains as well. As one of the part of the swarm intelligence, we have been working on how these primitive robots make the decisions while sharing very minimum amount of information with each other. So if individual robots have really limited range of communication and sensing, and they can only exchange a very limited amount of data with each other, because again, the goal of swarm robotics is to achieve a more complex and higher level intelligence while individual robots are simple, primitive, with limited processing, communication, and sensing capabilities. So this is one of the example of like each robot with really primitive capabilities. They have, for example, the visualization is only for three different options. If you have 3 different options, and they collect the information of these 3, and then how they converge to one option that is actually the best out of 3. And also this algorithm works for example, hundreds of options with thousands of primitive robots. So that's how we want to achieve in terms of the swarm decision making. Also, multi-robot and swarm applications can be used for area coverage. So if you have an unknown environment, or if you have a large warehouse that needs to be covered, and then these mobile robots should be dispatched to form a sensor network. So the actual kind of, the area coverage or task allocation among those robots are important. So this is one of the examples of how multiple robots can determine what task they need to do, and then how to reach to the assigned task area and form a closed sensor network. So since many of our research topics involves multiple robots or even a swarm, so as a research lab, it's hard to have a swarm of actual working robots because, again, the space restriction, funding restrictions, and so on. But your algorithm and whatever we develop in terms of the software should be applicable to the real robots, but the actual demonstration done only in simulations have a significant real to simulation gap. So what we often employ is actually hybrid simulation. So we actually implement multi-robot or swarm algorithms in simulations that runs in both physical robots as well as the virtual robots. They share the same type of information, and they perform collective tasks together in between the physical and the virtual ones. This is an example using 2 real robots and probably 13 or 14 virtual ones. They basically do the task area allocation and the coverage control problem together. Another example, whenever you have more than 1 or many robots, how you will establish the interaction between humans and the swarm. So this one was another DARPA-funded project to establish human swarm teaming simulation environment. So this visualizes actually a swarm planner creating the mission. So basically with the smaller map, that miniaturized map of campus that is shown, and then virtual swarm is visualized there. But those swarm is basically operating in a real world. So virtual robots forming a swarm that is mapped into the physical environment, so that you can see the tacticians' viewpoints that the person is wearing a HoloLens. You can visualize the real surrounding environment together with the virtual robots. They are performing a swarm missions, and you can actually visually understand what they are doing, how the task is being performed, and also what is the progress towards the actual completion of the mission. So as we completed these 2 DARPA projects, building new type of robots and human swarm teaming kind of a simulation and algorithms, we are, as the first real-world application of those swarm engineering and swarm intelligence algorithms that we have been developing was actually into agriculture. So I was actually talking to the 2 directors here right before this talk. So I moved to Texas in 2019, and I was with Case Western Reserve University in Cleveland. I've never been to a farm. I believe I have been probably a farm when I was a child visiting my relatives, but I've never been lived in a farm or any farm environment. And agriculture was kind of far from my areas. I was working on defense applications, urban military operations, and things like that. And then after I moved to Texas, I see so many people working in agriculture side, and then I see farms and different crops growing, cows and all those environments. So I saw a variety of opportunities to collaborate with people from agri-life, and also I see the diversity. Even you have the same type of crop fields, when you go to the farm A and B, they are different. And they operate differently, and then they have different soil conditions and different terrains. You need the actual robots to adapt to those kind of environment. So we proposed this concept to National Robotics Initiative program, and that was subsequently funded by USDA NIFA. So we are currently working on developing a configurable, adaptive, and scalable swarm that can be used for agriculture. So this is some of those kind of video footages of our robots dispatched to a farm, and the actual user, basically using a user interface, assigns a farm to be scouted. Then the robots determine, and then they basically communicate with each other, decide who to go where based on the actual physical size and capabilities of individual robots, because we have 2 different robots dispatched here. And then once that task allocation is done, the robots are sent to the farm, and then they start doing the scouting task and collecting the images. So far I kind of covered how we applied basically design-driven innovation applied in advancing technical and functional capabilities of robots. And I want to actually switch the topic to design-driven innovation that is inspired by origami. Origami is an ancient art that basically creates a space from 2D to 3D. So many of those origami designs, they might be just a static figure, but some of those designs, they allow actually some of those motions can be accommodated by those folded patterns and creases, so that you can see, like, some you can actually play around like a widget. One particular design I would like to focus on today is this one. It's called the Twisted Tower. It's not something I invented. It's invented by a Japanese origami artist. So this design, this specific type of origami is called action origami, which means it can actually generate the motion. And also this is a modular origami in the way it's not only made out of one paper, it uses multiple papers that is actually folded together and assembled. So the actual design has, so the structure is relatively rigid, yet flexible to accommodate fully kind of, it can actually collapse and extend, and it can twist and bend. There's no existing robotic mechanisms that can do. So this one was actually a great example of what origami-inspired kind of mechanism can do for robotics. So what we did was actually we folded the Twisted Tower and then added some of those kind of sensors, actuators, and then build a robot. So the actual same Twisted Tower demonstrated as a robotic arm, and then it could be used as a crawling robot. And we also folded the smaller fingers to build a robotic arm with the fingers so that it could be used as a manipulator and robotic hands as well. The same structure could be used as a reconfigurable wheels, so that could go on the ground as well as a water surface, so that can actually generate the different types of locomotion as well. So this one was actually, so hold this thing with the paper folded kind of, the origami designs. It started as a hobby fun project. So one undergraduate student came to my office saying he's interested in doing some research. I said, what are you interested in? And then he said, I like doing things and then doing with hands. And that student said, actually, I did some origami things too. So I said, origami has been always my interest when I was young, and why don't we explore some options of using actually origami for the designing? So that's how we started whole this process of actually studying. So he started folding those, and then we made it into a robot. But this work actually was presented at one of the largest robotics and the most premier robotics conference, and it attracted a lot of kind of interest. And then many people came to me what's next? I didn't have any idea what's next because, again, in order to fold this tower, you need 24 pieces of paper folded together and assembled for the first layer. And then you need 16 papers to be folded for each of them. So you can see hundreds of papers. So basically, you have highly motivated and talented graduate and undergraduate students sitting down in the lab for hours and folding this. It's not something that is doable, and not everyone could fold a smaller structure. So it requires a really high delicacy. So it's not something that you can do into a research problem. So we actually changed it into so we actually explored, now it's time to explore an option to see how we can do research with that one. So 3D printing is a uniquely suitable method for fabricating this highly complicated structure. One part is that this Twisted Tower has, when you look into the virtual plane of the top and bottom, so whenever it actually folds by twisting, the top and bottom space, the actual polygon shape do not change. That means you can actually apply a traditional rigid body kinematics. That is something that we, all the robotics engineers would know. So you can apply that one to describe the motion of this mechanism. Also, we can further engineer because now we're not restricted by papers. Now you can actually 3D print. That means you can further engineer and allow the design to be customizable. So if you have a base polygon using octagon, once you fully close, that's going to generate the twisting angle of 2 pi 360 degree divided by 8. When you use hexagon, so full twisting, so one layer of the tower will generate the 360 degree divided by 6. So you can actually achieve 60 degree of twisting. If you use a square, it's going to be 90 degree. So depending on what geometric shape you're selecting, the actual motion accommodated by each layer of this origami structure can be determined. So you can go as low as 3, and then you can go as many as whatever polygon you want to do. When you do the 3D printable designs, you want to actually apply certain types of analysis. You could, depending on how you design this structure, while maintaining the exact kinematics and motions and shape of the paper folded origami, there are many ways to do it in different ways. So here, one of the design options is basically designing those surfaces that remain unchanged and all the hinges and creases using soft materials, and those are connected. And the other one is all those trapezoidal shape that is forming a wall, forming walls of the origami designs, but it's all fully covered by soft materials. So the stress that is applied to the hinge and those folding areas, they are different depending on, these are exactly the same design, doing the same range of motion, but the stress applied at each of those critical points are different. So it's most likely the first design will be more like susceptible to cracks or damages compared to the second one. So this is another engineering point of how you convert into it. So as you can see, this paper folded one shown on the top, the bottom, that is 3D printed using two different materials of rigid and soft material that is printed using by a polyjet machine that uses the materials that is polymer composites. So you can select the different flexibility and you can print using two nozzles simultaneously. So this entire structure is printed at once. So it's no more folding involved. And then you basically need to input and there's press the button and then 3D printer will actually come out. You will have to do a little bit of after processing because this kind of structure cannot be printed without support materials. So you will have to put this one in the solvent to remove those materials, but it's very minimal human intervention involved with this one. So now it gives us an opportunity basically to how this can be manufactured, fabricated, and used for various applications. And also the quality of the design and the actual final outcome will be maintained, unlike the human folded, paper folded structures. So this work was featured at CNN Tech a few years ago. So you can see the robotic arm that is using actually 3D printed origami structure. It uses the soft material that is visualized with the black color, and then the rigid materials is clear plastic. And then we just added a simple gripper just to demonstrate this can be used for a robotic manipulator arm. And again, this kind of design, once you build a robotic arm, you can scale it down because again, converting into the 3D printable design is whether you can actually customize and scale it. So we actually used a smaller version of that one, 3 of them, to build a soft robotic hand. So we call it twister hand. So one particular aspect I would like to highlight is this robotic hand has no sensors. It has one motor that has, so 3 fingers with the cables running on each of them that is tied together, and then that is connected to the pulley of a motor. And then whenever you turn the motor, they close and open. So this kind of semi-soft robotic gripper eliminates completely any touch sensors that is required. In many cases, if you have a robotic hands with the rigid grippers, In order to grasp anything fragile or irregular, you need very complicated closed loop sensors that is required for actually manipulating it. However, this one is basically doing a simple closing and opening operations, while you see the finger's shape is different whenever it grasps an object, because again, the flexibility of those fingers, they wrap around different shape of the object, and then they grasp it in a different ways so that the finger deforms around the different object depending on the weight, texture. Instead of the robot actually have to analyze and detect and then basically generate the sensor-based control. So this one is actually what we want to show, the simplicity in engineering. You want to eliminate a lot of kind of, complicated codes, complicated sensors, and additional actuators by having simple mechanical structure and then semi-soft mechanisms that is design-driven that can basically replace a lot of those complexities. With the proper and further research, we are envisioning this kind of robotic arms. You can see it's fully collapsible, lightweight, and also it has a really large workspace compared to the size and the weight of the robot. You may envision it can be used as a wearable robotic arm. You might have your third arm connected to you. And also it could be used as a space robotics applications in, for example, if this structure is built really large, compared to those like a really heavy, bulky space robotic arm, you might have a collapsible structure. And whatever that goes to space, the weight and volume are the two critical factors that affect the cost the most. So anything foldable, lightweight, that would have a great potential for that. Agricultural robotics, again, the flexibility that can accommodate the actual different shapes and different needs in manipulation in agriculture environment. And also, I have actually received significant interest from medical and surgical, applications and doctors. They were interested in adding additional degrees of freedom for those, surgical tools, because again, whatever that goes in, if you have more freedom inside, that will reduce the actual size of the incisions and also basically the need for additional robotic tools. So I'm envisioning basically with the proper design, and that is connected to the material properties and also how the optimal fabrication technologies can be applied, then we can tackle the technical and engineering areas of sensing, actuation, and control that can lead to any of those applications and beyond. So since origami is always kind of fun topic, so I brought this one to my classroom. So in 2024 spring, the actual project topic was a paper origami robotic garden. So each project team should have are required to build some piece that you are expected to find in a garden. So you can see the origami peacock robot, and you have seen some of those robots, but they have all some of those additional requirements. So some of these flowers, they bloom with the lighting on the top, and sometimes they have the different sensors that is detecting the motions of the users, and then they activate the actual motion and blooming and closing as well. And some team actually came up with the idea of having, when you pour the water, then the flower will emerge and then grow into a full blossom. So with this I actually posted this video in LinkedIn to showcase what we do in the classroom. And that connected me to my old friend from graduate school. So there was a friend whose name was Carol Relly. And she is working as a creative, I believe, director, or working with San Francisco Symphony. And she was organizing a soundbox event that is held at the symphony to bring robots and music together. And then she was putting a concert together that is bringing AI-created music that is played by San Francisco Symphony artists. So they basically play those music, and then they display AI-created the visualization on the background. And at the same time, we had several exhibitions of robotics and other art forms that has more technical side of the interaction as well. So that led to an independent project with a group of students, so including both undergraduate and graduate, initially recruited from my class that was actually, I just showed you. And that led to the project The Bloom. So I will show you some snapshots from the event, so Soundbox event. So this one was, again, it's very different form, and it's not too much of robotics inside, but still the actual component technologies of robotics are there. So many of those are more of like arts and crafts type of project, but still it has sensors to activate the actual motion and different lighting of the colors when the person comes in. And it has also kind of, we have opportunities to incorporate many different types of sensors as well. But it was really well received by the audience by having some kind of, colorful display and then with something moving. Whenever you have anything that is physically moving and then with a great visualization, it always attracts people. And also that triggers a lot of kind of, interesting questions as well, how you can make this one more interactive and then what's next and then how we will kind of, proceed for more of these concepts of robots plus or cross art. Building on that one, this last May, so we participated at ICRA, that is the robotics conference, and the event was for art in robotics. So this one is another version of the art, but we actually added an interesting twist to it. So we added a HoloLens to visualize virtual butterflies. So this is the view that the actual person, user wearing a HoloLens can visualize. So this one, again, it was kind of, side project. We didn't have enough time to implement a lot of things, but at least we were able to put the butterflies so that the person wearing a HoloLens can actually capture a butterfly that will be randomly flying around. And then you can actually put it on the bloom flower. So this one, again, whoever comes in, they wear a HoloLens, and when they actually see the art piece, they were still interested, and then they were saying this is beautiful and very nice. And when they put it on, and everybody said it's completely different environment experience, because we put some kind of very the calm music, so you could kind of surround yourself in a completely different environment. You have those beautiful butterflies flying around. You could actually pick it up and then move and then place that on a flower that you choose. So after you place all of them, you will have those bloom that is basically a robotic flower, paper flowers. They are blooming and closing with the different lighting patterns behind. And then you have the butterflies that is kind of flapping wings as well. So this is the team. So what's next? So I wanted to take this opportunity so that I can actually shout out what's my plan, and if anyone is interested, please let me know. So I want to build an ant box. So I showed you this one. So this one was my swarm consensus algorithm. So what I want to build is basically, imagine you have a clear box filled with little tiny robots with LEDs that is changing colors. They're all moving randomly. And then whenever a person comes in or touching their hands, and those signals certain kind of preference options, and then it's going to actually visualize those consensus towards different options, but with the actual physical movements of those kind of little robots that is in the clear box. And also, it could actually make it interactive art with multiple people. They are basically participating with some of those sensor mechanisms. So if you have like 3 people, they are holding these sensors, and then they might compete with each other, and then what robots converge to whose decisions or whose preference could be one piece, but also just having a randomly moving kind of, the robots with the LEDs, that lighting will be converging, or they might sync, like similar to fireflies. So those kind of visualization is my next plan that I just came up with while putting this together. So actually you gave an opportunity for me to kind of consider my next project. So you might see, maybe if you invite me again next time, I might have this clear box with a ant box with lots of like robotic ants inside, or I might have to call it firefly box or something like that. with that, I'd like to conclude my talk, and thank you very much for coming here and then inviting me again.
Thank you so much. We'll transition. Go ahead and take a seat in the middle, and I'll give you a mic, and we can continue our conversation. Fantastic. Okay, great. Well, Waryang and I are going to join you, and as our discussion works, we spend the rest of the time. If you all have questions, we are most happy to take questions from you, but I also have tons of things I can ask as well. So as you maybe get questions going, if you'd like, I'll start with, first of all, thank you so much. And the Ant Box, I think, open invitation. I can, just looking out here, I see a lot of people that I think might be interested in getting involved in that. I would love to ask you to begin, in your process, do you feel that you separate out design thinking from build thinking? And if so, what kinds of ways do you find inspiration in that way?
I think that's one of the most difficult questions I've ever heard in my career.
Sorry.
So how do I do it? So I think it's a lot of, I think many people might agree or disagree. So a lot of design kind of, inspirations just comes, I think, instantaneously.
Okay, yeah.
And sometimes, and how it develops and engineer that into something functional or useful, that takes time. So, for example, for the transformable wheel design. So one, of course, I was thinking about some ideas along that line, but one day I just came up with that idea, but actual engineering and development into a robot that is done as a teamwork. And also for other kind of, the robotic art and those kind of things, it might, so some of those ideas might click, but actually what it materializes and then how it comes into life, it all comes with students and my colleagues, and then we work together. So probably that's the difference from an individual artist versus as a person who is working and surrounded by many students. And also my primary goal and research objectives is in engineering. So we often bring, I think the artistic or design inspiration always helps the engineering to be better. But how it is done, I do not have any clear answer for that, because again, every project that comes in a different ways. But I always try to incorporate some design aspect and also kind of aesthetic aspect as well. But it doesn't always happen. But whenever I have an opportunity, I try to do that.
Yeah, thank you. And kind of a follow-up, in the beginning of your talk and just now, you talked about if something looks good, it works better. And I wonder if you might expand on I mean, we sort of know this, but why? I mean, can you tell us a little bit more about that concept as you believe it to be true?
Sure. So it's like always, whenever you build a robot, you start with a prototype, and then you start building with something like, simple 3D printed or other parts that is available for you to quickly put them together, and then you have hanging wires and those the sharp edges and things like that. It always causes problem. So it's as you go and make it nicer looking, that always comes into a play of kind of, first cleaning up wires or cleaning up all those unnecessary sharp edges, unless it is intended for that one. And also kind of, having some of those curvatures that you might consider so you might optimize for the engineering design that actually make it looking better too. Like, nice car designs as well. They are all based on aerodynamics, but at the end it actually is done because of the performance. So I think many of those aesthetic features, they are also driven by some nature driven optimum kind of the shape. So I think it's some of the aspect I'm considering. So whenever that is looking better, if you have two robots, one is looking better, it's always go with that one.
That's fantastic. Are there any questions to get going that anybody has? Yes.
Yes. First of all, really, really interesting stuff. One of the things I was wondering, where you were talking about the applications of the technology, particularly the twisted arm. For some of the examples we're showing, have you ever considered how this might be used in the realm of those with disabilities? And I was actually thinking of the initial that can actually climb steps. And I was thinking, wow, how could this be used for those who use wheelchairs or motorists or things like that?
Were you able to hear him?
Yeah, I think you mentioned about how to use those like designs into different applications.
Particularly disability rehabilitation.
Yes,
Have you
yes.
thought of that? And
Yes. So that's a great point. And then one of the areas about the twisted tower actually. So one doctor actually, when I was in Cleveland, he reached out to me and interested in twisted tower because of that design and the damping capabilities. So because it is like a spring damper kind of behavior. So those things for the prosthetic device. So it could, because it's additional degrees of freedom, so it can accommodate the damping, like the actual shock absorption from different angles. And so that is one of the area. And also the wheelchair is one of the areas that we have explored as well. Again, that there are many engineering components to be considered for those, like, whatever that is carrying a human, but that is an excellent point. And then we are also interested in those applications.
Thank you so much for your amazing presentation. I have a question about your class, like dealing with origami in the classroom. I was wondering how engineering students responded to the class project. They have to actually like fold, origami and also incorporate some sort of art and crafts into their engineering project. I was wondering, if they are open, they are open to different approach, not just like circuitry or wires, but incorporating some different materials and different crafts ones. And extend to that question, I was also wondering, maybe we can also team up with some of our art classes and then collaborate with your students and then do like really a robotic design with maybe music, maybe like other visualization. So that's a question.
Thank you. I think that's a great point. And believe it or not, all engineering students, when they are given an opportunity, they like to explore and more kind of, to incorporate the more artistic side and something different than those. I'm not gonna say that everybody's good at, but they like the idea of incorporating something kind of non-technical side as well. So I cannot speak on behalf of the students. They might have complained a lot with additional or too much work they had to do, or just their team couldn't figure out nice origami designs. But in general, I received a lot of kind of positive feedback directly from the students, and they love the opportunity to actually incorporate some of those, like origami art or those kind of some creative ideas into the course project that they had to bring, like sensors, actuators, controllers, and wireless communication, those aspects. That is one of the requirements, but they have to wrap them into the form of origami art. So if it's not like every year I have the same project. Each year I have different project. So this year they're building a actual robotic hand. So they're gonna come up with different 3D printable designs that can be mounted on a robotic arm, so they can manipulate different objects. But again, I think the great opportunity, so there are unlimited opportunities when the artist or the designers or with the students, like in your college, collaborating with our students, because again, they're gonna kind of ignite, and then they're gonna like leverage their skill sets and then come up with something really creative. And especially, I think, it could be in a formal classroom settings, but also it could be some independent projects as we did for the Bloom. So that one also, we only included all mechanical engineers. So I was the one who is actually making it a little bit pretty, but all the work actually done by the mechanical engineering students. So you can see how these kind of simple, relatively simple project can go to the next level when we involve the students, who has the actual major or who has the skill sets and this kind of, designing skills that can work together.
That's great. Thank you so much.
Do we have any other questions? Yes.
So first off, just reiterating, insanely cool work, but also just from my basic understanding of robotic swarm, which is kind of like machine learning, where they're learning from each other behaviorally. How are you incorporating or like adjusting for any personal bias that the user might input towards that behavioral application, especially especially once you're moving away from looking towards like solving the problem more based on like appropriate design, which subjectivity and interpretation once you move with art.
Did you hear her?
Yes. So in our swarm robotics, there is no kind of human, so that the specific algorithm that I showed you, that there is no human involvement. Of course, the setting of the problem involves humans of what are the options available, but their decisions are done autonomously by individual robots, but at the end, the algorithm allows them to converge to one decision. However, in any of those machine learning based approaches, they involve the actual bias. Typically, so if we are talking about data-driven machine learning, that is training a model with large amount of data. Depending on the data, of course, the model will be different. So a lot of bias that might be either coming from whoever choose to train in a specific way, so that might be human kind of influence there too. The data set itself has certain bias. So if you have, so for example, our robots needs to navigate in diverse environments. So our robots must have the perception capabilities. So we are training the robot model for terrain classification. So using an existing set of data, so depending on where that data set is created, that is trained for that one. But your robot might operate in a completely different environment. Then the actual classification results might have significant kind of errors. Then it may not be useful. Then you will have to retraining or do additional kind of layer of the algorithms as well. So those are kind of limitations. But again, how you will cope with those limitations by introducing some online tuning or parameter tuning algorithms, or different approaches to kind of detect what is uncertainties, like how much uncertainty is involved with the actual outcomes. So that can mitigate it. But again, whenever we are talking about human bias or the actual trained model in AI, there is no kind of concrete solutions that will remove all those problems yet.
Other questions from you all? Yeah, go ahead.
Thanks also for your excellent talk and introducing us to your research and hopefully inspiring collaboration. I'm particularly excited about your origami and also kind of the natural references. So you use the flower in terms of the origami. Then you also talked about ants in terms of a possible project or fireflies. So I wonder if there's also any inspiration from nature. Are you actually looking at flowers and how they bloom? Are you looking at ants and how they kind of create colonies, or possibly at fireflies?
Thank you so much for a great question. So a lot of actually swarm robotics research is driven by swarm behavior of those ants and kind of the swarming insects as well as animals. So while our particular algorithm is not driven by biological kind of inspiration, but many of those swarm behavior actually after making the decisions how you move from one point to the other one. So foraging behavior of ants and other things could have been actually used for a lot of swarm robotics research as well. So those could be a great opportunities for kind of, for extending from ant box ideas. So it's not necessarily only visualizing with LEDs, but it could be actually behaving in a certain forms, and then with the simple rules, whether they can collectively merge into one direction or they may change the shape. So those kind of things could lead to some of those biological inspirations is actually created and integrated into the art form, but also like the fireflies. So when they start with random lighting, but when you observe longer, they kind of start synchronizing. So those kind of things can be actually great example of how we can incorporate the biological inspiration into art or art plus robotics projects. Thank you.
Speaking to collaboration and possibilities for the future, how might you envision some of that? I mean, would you like for people to just contact you with an idea? Is your lab able to take on side projects regularly? Is the classroom the better environment? What's best?
I think I'm open for every possibilities. So I actually have this vision of creating, so my research lab is called Art Lab, but but I am kind of dreaming of the idea of having an art studio. So it's Adaptive Robotics and Technology Studio that allows the creative robotics art to be kind of, that can accommodate a lot of like students, faculty come together and build things together, explore ideas, and bring kind of, the new project together. So that's something that I'm envisioning over the next few years. I don't know how it can be materialized or not, but I think the concept is there. I can put a virtual art studio online, so that's something we can do. But again, anyone interested in exploring further or kind of having ideas that might involve some robotics inside, so I'll be happy to talk, and I'll be open to any kind of potential conversation and discussion.
Fantastic. Thank you so much. Any last questions from our audience before we break? Well, yes, please.
I was just curious on the class project with the students. Did you give them any background on like the history or information about kinetic art and how that could inform their projects? Or was it just like, here, make art with this and unleash them?
I gave a little bit of background on kind of origami and how origami has been inspiring in some of those research work and the robotics side, but not necessarily going with the kinetic art and all those things, because it could open up a lot of discussions. But again, this course is Introduction to Robotics course, so it's very well structured ones, but not much of room to kind of introduce a lot of different concepts. But again, the kinetic art and origami and those kind of, the kinetic art can be actually the next year's project topic. So thanks for giving me the idea.
Well, that's fantastic. Well, Kiju, thank you so much. The ideas are flowing both ways, it seems. I think that there's a lot of energy, and thank you all for your attendance and for your fantastic questions. Please enjoy. We have a reception available if you'd like to ask Kiju some additional questions or interact with her more, and then we'll look forward to seeing you in October for our next talk. Thank you so much, everyone. Have a great day.